Hello everybody, myself Dr. Gaurav from Government Degree College, Paloda. Uh, we are in the semester first, unit number 2. In this particular lecture, we shall study one of the most important theorem as far as partial derivatives are concerned, that is Euler's theorem. And Euler's theorem is restricted, that is applicable only to a special class of functions which we called as homogeneous functions. So first of all, let me define what's a homogeneous function. Here, the number of there is no limit to number of independent variables. We can have n number of independent variables here, but as far as we are defining in this particular context, we are restricting ourselves to two variables only. So here the target function which we are taking z, we are considering it as a function of two variables. Although the definition of homogeneous function, we may extend it to n number of variables. So here we shall restrict ourselves by taking z as a homogeneous function of two variables only. So a function z is said to be homogeneous of x and y if it can be expressed in this particular form. That means if we can write z as a function of this form xn, some function of y upon x, then we say that z is a homogeneous function, and here the number n, it's called degree of the function. Note that this number n can be positive, it can be negative, it can be a rational number. For example, z equal to x cube minus y cube upon x minus y. Here we can rewrite numerator as x cube into 1 minus y upon x whole cube, and we can rewrite denominator as x into 1 plus y upon x, and which in turn can be rewritten as x square into some function of y upon x, where this particular f y upon x is equal to 1 minus y upon x whole cube upon 1 plus y upon x. Here you can see that leaving this x square, the rest of all the quantities, there is no term of x alone or no term of y alone. Every term is in the form y upon x. So it's a function of y upon x. That means we can write z as x square into some function of y upon x. So z is a homogeneous function of degree 2 here. Or we can say that z is a homogeneous function of order 2. Now it's a very important easy exercise to check that if z is a homogeneous function of degree or order n, then certainly their first order partial derivatives, that means del z upon del x and del z upon del y, they will also be homogeneous function but of reduced degree. That means they are of degree n minus 1. So let me give a formal proof to it. Suppose z is a homogeneous function of degree n, then certainly by definition z can be written as xn f of y upon x. And if you differentiate it partially with respect to x, then del z upon del x will be first function into partial derivative of second plus second function into partial derivative of first. That means the product rule for differentiation. Now this is xn. This is, it should be like this, xn f dash of y upon x, and then derivative of y upon x is minus y upon x square because y is treated as constant here. So the derivative of 1 upon x is minus 1 upon x square plus f of y upon x, and derivative of xn is nx n minus 1. And if we rewrite this, there xn is in numerator and x square is in denominator. So this is x power n minus 2 minus y is taken here. So this is f dash of y upon x plus nx n minus 1 f of y upon x. And if we take x n minus 1 common, here I am writing the second term in the here. This is n time f of y upon x, and since x n minus 1 is taken common here, so this is y upon x f dash of y upon x. And you can see that this particular term, here you can see no term of x alone or no term of y alone. Only if they are present in the terms of y upon x. So this whole is a function of y upon x. I'm writing it as phi of y upon x. So we can see that we are writing del z upon del x as x power n minus 1 into some function of y upon x. So by definition, this is a homogeneous function, but of degree n minus 1 now. Similarly, we can show that del z upon del y is also a homogeneous function of degree n minus 1. It's simple, since del z upon del y, here xn is a constant. So we are keeping as it is. The derivative of f of y upon x is f dash of y upon x, and since x is constant, so we are keeping 1 upon x, and derivative of y is 1. So this is like this. And since f dash of y upon x is a function of y upon x only, so I am rewriting it as psi of y upon x. So you can see that del z upon del y is of form xn minus 1 into some function of y upon x. So again, by definition of a homogeneous function, del z upon del y is a homogeneous function of degree n minus 1. Now let me come to, as I have told you earlier, one of the most important theorem as far as partial derivatives are concerned, that is Euler's theorem on homogeneous function. So this theorem states that if z is a homogeneous function of x and y of order n, then x time del z upon del x plus y time del z upon del y is equal to n time z for each point on which z is defined. Again, I would like to add that we may take here, instead of 2 variable, we may take 3, 4, 5, or any number of variables. So the Euler's theorem hold good for 3 variables, 4 variables, 5 variable, and any finite number of variables. But as far as our scope is concerned, our syllabus is concerned, we are restricting ourselves to 2 variables only. So it's one of the most important theorem as far as partial derivatives are concerned. Since z is a homogeneous function in x and y of degree or order n, so by the definition we can represent z as x and some function of y upon x. Let me name it as equation number 1. What we have to do, basically, we'll have to differentiate this z first partially with respect to x and then partially with respect to y, and then multiply the obtained equations by x and y, and then add the two equations. The result should be nz. So let me try it. Now z is of this form, so del z upon del x, as we did earlier, will be of this form. Now multiplying both sides by x, what we'll get, x time del z upon del x is like this. And since z is xn f of y upon x, so I am writing z here. So this becomes z minus this term. Let me name it as equation number 2. Again, from first, as we did in last exercise, del z upon del y will be like this. Now multiplying it by y, we get y time del z upon del y is equal to y times xn minus 1 f dash of y upon x. This is equation number 3rd. Let me name it as equation number 3rd. Now adding 2nd and 3rd, here you can see that this term is positive here, and in the equation number 2, same term appears here also with negative sign, and here it is with positive sign. And if we add these two equal and opposite terms, they cancel each other, and we are left with what? We are left with this particular term, that is nz. So x time del z upon del x plus y time del z upon del y is equal to nz. In the next lecture, we shall verify Euler's theorem for some particular functions, and we'll see that what is the result of this Euler's theorem hold good for those particular functions. Thank you very much.